Okay, so we're continuing with related rates. Here are a little bit different problems, but still things that you could do. Some of the formulas you might not remember, so you might have to look them up, but that's okay. So looking at this one here, we're talking about a spherical bubble. And so anything, the volume of a sphere is 4 pi over 3 r cubed. And so the volume is increasing at a rate of 9 millimeters cubed per second. So we know, again, they're telling us it's volume and they're telling us it's increasing in a rate. So we know that that is a derivative. So when I look at this, I know that we have the information there. I'm just going to put it down here so we know the information. We know that we're given dv dt. I'm going to change that and erase this. Okay, so dv dt is going to be 9 millimeters per second. A little bit too many humps there. Per second. And so we're given that information. And if we keep rating at what rate is the radius decreasing? So radius. So we know we're going to have to find dr dt, and this is all with respect to time, not x or anything else. So we know we're doing dt, not to mention that they tell us that it's seconds there. So we don't know what that is when the radius is going to be 3. So we're given that the radius is 3 millimeters. So this is the information that we have, which is great. And here's the problem that we have. Here's the volume. We have the r, that's the only variable. So the only thing that we need to do is dr dt, and that's finding the derivative. So we're going to take the derivative of the volume. So we know when you take the derivative, we are going to have dv dt, because you're taking the derivative of the v, and then the 4 pi over 3 is the coefficient, so we leave that alone, 4 pi over 3, and we take the derivative of the r, and the r is the chain rule, so it's going to be times 3r squared. We leave the r alone, that's the inside, and then we chain on the derivative of r is going to be, so that's the inside, and it's going to be dr dt is the derivative of the inside. So if I manipulate it a little bit and make it much easier, this 3 and that 3 is going to cancel because that's over 1. And so we end up with 4 pi r squared dr dt. Sometimes I sound like a pirate, dr dt. Okay, so here we could fill this in and find this information. We want dr dt, so I know that this one here is going to be 9 millimeters cubed per second, and it's going to be divided by 1 over 4 pi r squared, which is going to be 3 squared, because I want to multiply that. So that's all I'm really doing, is because this here is a fraction, I'm going to multiply that by the fraction there. So what we do is that we're going to take this and do 1 over 4 pi r squared, and then this is over 1, so that cancels, so I do 1 over 4 pi r squared to that side as well, and that's what we get here. The dVt is 9, dV dt is 9 millimeters squared per second, and then when I move this over, I get the 1 over 4 pi n square, and then we end up getting the dr dt by itself, which is what we want. And so this is going to be 9 that cancels with that 9. And so we end up getting something that's really small here, 1 over. And then the 3 inches is going to be millimeters squared. So that's going to cancel there. And so we know that it's talking about the radius. So that's just going to be 1 unit on there. So we end up with 1 over 4 pi millimeters. Notice how there's no units, which makes sense because it's just a long per second. So you always want a sentence with this, and you want to change it to a decimal because that's when it says there. So the radius is increasing because it's a positive answer at the rate of 0.08 millimeters per second. And so That makes sense that it's millimeters because we're talking about a radius, which is a distance there. And so that would be your sentence. And there we go. So that's how you do that problem on there. Let's do this one. This one here, it's a little bit different. It's something that we've done before on your last project on there. The particle moves on a curve, and that is the curve that we're talking about, such that the dy dt is equal to 6. So this is the rate at which the y values are moving. And so they're giving you no units. We'll just write down units on there, 6 units. Find the instantaneous rate of change of x with respect to. So we want to know what we're really finding here is we want to know what dx dt is when x is equal to 2. And we're given the information dy dt is equal to 6. So we're given the rate at the y. We want to find out how the x, what rate the x is moving when x is equal to 2. And here's the equation of the curve. So of course we're going to have to take the derivative. So we have y is equal to 4 x plus 1 squared plus 3. One of the things that you need to notice is that the 4 is just a constant, so that's going to make our life a little bit easier. This is doing the quotient rule on here and implicit because you have that y over here. So what we get here is that we're going to get dy dt, and it's a mixture of the chain rule and the quotient rule. You could do the quotient rule, and that's going to look a little bit crazier, but because this here is just 4, what I'm going to do is I'm going to say 4, and I am just going to move the whole thing up on there because I could. And so we have this squared plus 3 to the negative 1. And that way I don't have to do the quotient rule and do all that work. Now, if you want to, you could definitely, but here I don't need to. If I move this one up, and it's a 4, so it's kind of easy. Either way, I would have to do the product rule, and the chain rule is embedded in there. Okay, so then we go dy dt is equal to, and now what you want to do is you're going to move this over and take the derivative, so we're going to get negative 4. And so we're taking the derivative of the outside, and that becomes a negative 2. And then we're going to leave the inside alone. So the inside is x plus 1. Maybe I'll do that in a different color. So we leave the inside alone, x plus 1 squared plus 3. And so we did the derivative of the outside, and now I'm going to take the derivative of the inside. So the derivative of the inside is going to give me here, it's going to be 2 x plus 1. And then the derivative of 3 is just going to be 0. And if it was something else on there, I would take the derivative of the inside, which we are. And so I'm going to change that so that you understand that that's what we're doing. And so we take the x plus 1 there. And so we take the derivative of the inside because we left the inside alone, which is the x squared. And that's going to be, when you chain it on, it's multiplication. So it's going to be dx dt because we're taking it with respect to t. So that's the chain rule. Again, you take the derivative of the outside, you leave the inside alone, and then you take the derivative of the inside and chain it along. The 3 becomes 0 because that's the derivative of a constant because it's plus 3, not the same as multiplication of the 4 like it is here. It's not a coefficient, it's just something that's added. And then we take the derivative here, so we bring down the 2. That's really a 1 there because you subtract 1 from it. And then we leave the inside alone. And because we're taking the derivative with respect to t, we have to take the derivative of x, which is going to be dx over dt. And that's really what we want to find is that value anyway. So we're going to take all this stuff right here, and we're going to be able to evaluate it now that we take the derivative, and we know dy dt is also that. So we're going to just fill everything in, and we have this to be 6, negative 4, the x is 2, plus 3 to the negative 2 times 2 plus 1. And then this is the one that we want to find, dx dt. So Okay, so the next thing we want to do is we actually multiply it out because it's just numbers and then subtract it to the other side. It turns out that we end up with 864 over 24, and it's going to be negative is equal to dx dt. So we have to write a sentence for it. And so in this case here, x is decreasing because it's negative at a rate of negative 36 units per whatever time. And that is your answer. Okay, so let's do one more. This one is always a fun one. This one here with the two trains. Two trains leave at a station at the same time, with one train traveling south at 20 miles per hour. So that's a rate. So we know we're talking about it. And the other one is traveling west, and that's another rate. How fast we want to find a rate is the distance increasing between the two trains after 3 hours. So at T, they're giving us that T is going to be 3 hours. So T is equal to 3. Okay, so when we're looking at this, they're giving us direction. One is going south and one's going west. So if we draw the trains here, one's going south and this one here is going to be 20 miles per hour. And then one's going west and that one's traveling 33 miles per hour. And we want to know the distance that the train is going. So we want to know this distance out here. How far is it increasing? So here, because this is going down, we're going to say that's y equals. And this one here is the horizontal. So we're going to say that's x equals. And x and y. And we're going to say that it's a right angle because it's south and west. And we're going to say that the hypotenuse is going to be z. And we want to know what's happening after 3 hours. So when t is equal to 3. So we have some information here. We know that if x is going at 33 miles per hour, when t is equal to 3, we know that it has traveled 99 miles. So 3 hours. Because the hours cancel, so we know that that's what it's traveling. And then we know that y is traveling at 20 miles per hour, and at t is equal to 3 hours, we know that that one is going to be traveling at 60 miles per hour. Or 60 miles. It has traveled 60 miles. And so we want to know, so that's what the information that's given to us. And we want to know how fast the distance is changing between them. So we want to know dz dt. That's what we're looking for in this problem. Okay, so how do I solve it? Well, because it's west and south, we know that it forms a right triangle. And so we know from this here that we have x squared plus y squared equals to z squared, the Pythagorean theorem. And so then we could just take the derivative with respect to time and then be able to solve it. So the derivative here again is going to be 2 x times 1, and it's going to be dx dt. Plus this one here is going to be 2y dy dt. And this one's going to be 2z dz dt. And, I am going to go ahead and mark that. And so this one here, the dz dt, is what we're looking for. So that's our goal, and that's what we want to find. Okay, so now we know some information. We solved all this information that we know here. So we're just going to be able to fill that in. So we are going to say 2, and then the distance that it would already have been would be 99 miles, and the rate at which it's going is 33 miles per hour. This is miles there. And then, so we fill that in, and then 2 times the y. The y is going to be at t equals to 3 is going to be 60 miles, and it's moving at a rate of 20 miles per hour. And then that's equal to 2. And then z, well, how do I know what z will be? Well, in order for us to do that, what we do, I'm going to erase this part here. I know that if this is moving there, I could fill this in, and this part right here, the 99, this would be 99 miles, and then this one here is 60 miles. That's how far apart we want to know what the value there is. And so we could find out what z is by doing that here. So we do the Pythagorean theorem, and where we have 99 squared plus 60 squared is equal to z squared. And when you do all that, it turns out that z is going to be 150 miles. Well, 115 miles is what C is going to be. So I could just fill that in, 115. Store it in your calculator, use the whole entire thing. That way it has a less marginal error. And so we have that there. And then we don't know what dz dt is. So that's what we want to find. So everything else is filled out, and so we just do some calculations, and it turns out that when you solve for it, dz dt is going to be approximately 38.5875 miles per hour. So it's an approximate because we rounded it. So then you need a sentence. And so the distance between trains is increasing because it's positive at the rate of 38.5, let's just say 9 miles per hour. And that is your problem. Very good.